Modeling methods and the degree of parameter uncertainty in probabilistic analyses of economic evaluations. This presentation is based on our publication in the Network Modeling Analysis in Health Informatics and Bioinformatics. Author contributions for this article. I thank my co-authors. The outline of this presentation. I will start with the background. Probabilistic analysis assigns probability distributions to model inputs to account for parameter uncertainty. Parameter uncertainty can be reflected in the standard deviation or the credible interval of expected and incremental values for costs and effectiveness outcomes. Probabilistic analysis is often presented by a cost-effectiveness acceptability curve and expected value of perfect information with a range of or a specific wiliness to pay threshold. The routine approaches for presenting probabilistic analysis do not make an explicit judgment of the degree of uncertainty, large or moderate, for decision-making. Committees making funding recommendations can find it challenging to comprehend the impact of uncertainty and appreciate its importance in deliberation and decision-making. Cran and colleagues proposed the Ontario, Canada Decision Determinants Framework to guide decision-making around non-drug-related health technologies. This framework included three main categories: 1 context criteria, 2 appraisal criteria, and 3 feasibility criteria, including budget impact and organizational considerations. This framework provides general guidance to end users and policy or decision makers to understand and interpret the degree of uncertainty in the economic evidence. Based on the Monte Carlo simulation results, this framework presented parameter uncertainty in economic estimates qualitatively, using 5 levels to describe uncertainty, including highly likely cost-effective, moderately likely cost-effective, uncertain, moderately likely not cost-effective, and highly likely not cost-effective. But the above framework does not specify for the modeling method and model input contributions to the model uncertainty, so it is mostly appropriate for typical cases. Thus, for non-typical cases, the strict application of this framework may not be always suitable. We sought to extend this general framework for 2 non-typical scenarios. Simulation Study 1. Intervention and control having different health states. A health economic model commonly consists of several health states. Intervention and control strategies often share the same health states, but patients in different treatment strategies have different probabilities of transitioning to these shared health states, with different durations of stay in these states over the study time horizon. In such case, common input model parameters are assigned to the shared health states in all compared strategies. However, in some cases, the intervention and control strategies may be associated with different health states. In this case, unique parameters are specifically assigned to a new or different health state created for one comparative alternative solely. For instance, treatment options for non-invasive, low-risk cancers, prostate cancer and thyroid cancer, include active surveillance, radiation therapy, and surgery, radical prostatectomy and thyroid surgery. Transition to some health states, such as recovery from the surgery and surgical complications, can only occur in the surgical treatment strategy. We observed that economic models considering different health states for the intervention and control strategies may result in larger uncertainty in the outcome estimates, a larger standard deviation estimate or wider uncertainty interval of the incremental effectiveness. We aim to provide mathematical explanations and examine this observation through a simulation study. Conceptually, we can treat the common decision analytic models, decision tree and Markov models, as the function of combinations of additions, subtractions and multiplications of variables. Then, We can start with the basic concepts of the variances for additions or subtractions and multiplications. When the intervention and control strategies have different, unshared, treatment health states, there is a greater number of variables for health state utilities and costs. The first formula has shown that the variance of the sum or the difference of variables would increase with the increased number of variables. For the multiplications, the product of x, y is related to expected values of x and y, in addition to variance x and y. But, if we contextualize two formulas, it becomes clear that, in general, the greater number of variables included in the economic model would lead to the greater variance. For example, Cowley and costs associated with the states can be obtained from health state utility and yearly or monthly costs multiplied by the durations of staying in the corresponding health states. After the multiplications, the health state costs and Cowley would be added to obtain the total costs and Cowley of a treatment strategy. Finally, the incremental costs and incremental Cowley between strategies would be calculated using subtractions of total costs and Cowley in different strategies. As eventually the health and economic outcomes in the economic analyses would be calculated by addition and subtraction, the greater number of variables, such as the treatments are associated with different health states, would lead to the increase of variance. We designed a simulation study and evaluated how the degree of uncertainty in model results changed if the intervention and control strategies had different treatment health states, compared with the case when the intervention and control strategies shared the same health states. We assumed that when each was compared with the control, both intervention 1 and intervention 2 would lead to the same health benefit in Cowley and associated with the same incremental costs. Intervention 1 and the control shared the same health states A and B, but intervention 2 was associated with two different health states, C and D. We compared the amount of uncertainty between these two cases through assessments of standard deviations of incremental costs and Cowley, and the cost-effectiveness acceptability curves. The details of study design, model and model parameters can be found in Supplement 1. We present results of the simulated cost-utility analysis in Table 1. Intervention 1 and 2 were associated with the same expected total estimates for costs and Cowley, while the incremental cost and incremental Cowley of intervention 1 or intervention 2 versus control were the same. The standard deviation of incremental Cowley for intervention 2 was 4 times higher than the standard deviation of incremental Cowley for intervention 1, 0.022 versus 0.005. We also presented the probabilistic analyses results using the cost-effectiveness acceptability curve. We plotted the probability of cost-effectiveness for intervention 1 and 2, compared with the control. The cost-effectiveness of intervention 1 was more sensitive to the willingness to pay threshold than the cost-effectiveness of intervention 2. For a willingness to pay of $50,000 per Cowley, the probabilities of intervention 1 and 2 being cost-effective versus control were 0.94 and 0.64, respectively. We defined parameters to generate same expected costs and Cowley for interventions 1 and 2. The simulation study showed that the degree of uncertainty in the cost-effectiveness results for the case of intervention 2, assuming different health states for the compared strategies, was much greater compared with the case of intervention 1. Although the findings of simulation study cannot be generalized to all cases, they suggest that assuming different health states for the comparators with the unique parameters may strongly affect parameter and decision uncertainty and decision-making. Simulation Study 2. Estimation of Cowley by area under utility curve from the summary statistics of post-treatment utilities. In economic evaluation, We typically define model health states and search for their utilities from published studies. However, for some diseases or treatments, such as migraines, it is challenging to clearly define health states. Also, many clinical studies report longitudinal health-related quality of life or utility post-treatment, but not the utilities for specific health states. The post-treatment health utilities may include mixed health states due to various levels of response and/or adverse effects in patients. In such cases, we can use the summary statistics of post-treatment utilities to calculate the area under the utility curve to estimate the Cowley over the model time horizon. An economic evaluation alongside a clinical trial to compare behavioral activation versus cognitive behavioral therapy for depression showed the incremental Cowley of behavioral activation versus CBT. Mean 0.05, 95% confidence interval, minus 0.046 to 0.145 over 18 months. We calculated Cowley using the area under the longitudinal utility curve reported and incremental Cowley from the probabilistic analysis. We found that the uncertainty interval of incremental Cowley in our probabilistic analysis was much narrower than that reported in the clinical trial. We sought to understand why the incremental mean Cowley from probabilistic analysis were associated with the narrower uncertainty interval compared with the one calculated from real-world individual-level data. Assuming that in addition to the baseline utility, U0, there are 4 follow-up visits for utilities, U1, U2, U3 and U4, at the 3 months intervals. The Cowley over 1 year can be calculated using area under utility curve method. Cowley are the linear combination of utilities. If random variables are positively correlated, such as the repeated measures of utilities, the variance of their linear combination, such as Cowley, would be greater than the independent cases due to the positive value of the covariances. However, when the information of correlations between visits is unknown, actually the correlation coefficient seldom reported in the publications and is not incorporated in estimating Cowley in the probabilistic analysis, we underestimate the true variance, or the parameter uncertainty, of Cowley. We generated the longitudinal utility data which incorporated the between and within subject variances of simulated individuals in 5 visits over 1 year in hypothetical trials. In brief, the findings of our simulation study reflected our observations in the motivation example and the mathematical explanation. This simulation study suggests that the uncertainty levels of Cowley and incremental Cowley are likely to be underestimated when the correlations of repeated measures in longitudinal data were unavailable and ignored. Thus, we need to interpret with caution the uncertainty level of estimated model outcomes that did not incorporate the correlation between visits when applying the summary results of longitudinal studies. Furthermore, the health utility studies need to report the correlation coefficients of utilities between different visits. Then, researchers can simulate correlated data and make more accurate estimates of Cowley. Based on results of our simulation study, we propose the following. If the key input parameters of an economic modeling study are unique, these model parameters are used in only one strategy and not in another, such as unique health utilities. It may be expected that the variance associated with various model outputs could be large. Because of this imperfect knowledge and estimation, we may need to tolerate a larger uncertainty level in decision-making. If a health state utility, X, is unknown, and we assume that 2 health states, X and Y, should be assigned the same health utility, then we need to simulate separately utilities for these 2 health states, X and Y. If the correlations between model parameters are expected to be strong, but the correlation coefficients are not available, we should also expect that the actual uncertainty could not be accurately captured by the probabilistic analysis. Researchers may conduct sensitivity analysis assuming different magnitudes of the between-parameter correlation to examine its influence on the model results and decision-making. In conclusion, for the probabilistic economic evaluation, the current framework related to a qualitative assessment of the degree of parameter uncertainty level need to be interpreted in the context of a modeling approach and assumptions used in an economic evaluation. This is to help decision and policymakers to properly account for uncertainty in economic evaluations and enable appropriate policy recommendations and budget allocations. Here is the timeline of this article. Thank you.